Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Last time we started to talk about factors and factor zoo, and we went through types of factors, and we said that factors are just tables that join together the probability of multiple variables. We went through several types, I think 5 types of factors, but we didn't say how we will use them to do inference, and that's exactly what we will do today, inshallah. Using inference by enumeration to show you the idea first, and then we'll go through variable elimination. So we'll start with an example. The example is a very simple Bayes net of 3 variables: raining or not, traffic or not, being late for the class or not. And it seems like being late for the class is major today. Anyway, so with that Bayes net, we will have 3 CPTs, right? 3 conditional probability tables, one for each of these nodes. So we have P of R, we have P of T given R, because R is the parent of T, and we have P of L given T, because of course T is the parent of L. So that's the initial factors. All of these are factors, by the way, based on the discussion of last lecture. These are factors. So we'll start with these factors. Now, if I want to compute P of L only, so that's the prior distribution or the marginal distribution of L, what we know how to do that so far is by doing the sum over the joint distribution. So I have to compute the joint distribution first of P of R, T, and L, and then we marginalize R and T. And that's general, by the way. Yani if I have 3 variables like that, I think I said that last time, if I have something like that, and I want to get probability of C only, so from the joint distribution, if I have the joint distribution of all the variables, I sum over the variables that I don't want. So that's marginalization to get the marginal probability of C. So that's what we have here. We sum over the joint probability over all possible values of the hidden variables, which are R and T here, to get P of L. Now, this is exact. I mean, this is the general case. We didn't use the fact that we have a Bayes net here. Once we know that this is a Bayes net, then we can express this joint distribution or this joint probability by the factors that we have. So we have P of R, P of T given R, P of L given T. And all of these probabilities are in the tables here. Okay, so that's the general way of doing something like this using the tables. We didn't say anything about factors or variable elimination or anything. That's what the mathematics tell us. Okay, what's the probability laws tell us. Now let's see how we can use factors to do that efficiently. So we'll track objects called factors, as we discussed last time, and the initial factors, as I just mentioned, will be the local CPTs, 1 per node. So we'll start with, if we are talking about our previous example, we'll start with P of R, P of T given R, and P of L given T. And if I know any value, if I have any evidence, then I will select from these CPTs the rows that match this evidence. So the initial factors should be, if I have plus L here, so there's no L here, there's no L here, but there is L here, right? So I will just cross out the ones that don't match the evidence, and I will keep just these 2 rows for that factor. So initially I will have P of R, it's the same, P of T given R, it's the same, and P of plus L given T, because I just selected the rows that match plus L. So that's the initial step, the initial factors that I will work on. Okay, so that will always be the first step if I do inference by enumeration or variable elimination. Okay, right. Now the general procedure is that I will do joining. So I will join all the factors. So that's, again, we are talking about inference by enumeration. We didn't talk about variable elimination yet, which is more efficient than inference by enumeration. We'll only now talk about inference by elimination. Sorry, not inference by elimination. Inference by enumeration, and then we will see how we can modify this a bit to do variable elimination. So the idea of inference by enumeration is to join everything, join all the hidden variables, then eliminate them, and then eventually we will normalize. Okay, join all factors, we get the join probability table for all variables, including the hidden variables, then eliminate the hidden variables, then normalize. Of course, the rest of the lecture will explain all of this, but this is the main idea. Join until we get all the hidden variables, then eliminate one by one to shrink the table and get what we want eventually by normalization. Let's see how we do that. The main building blocks in doing that are two operations, only two operations: join and eliminate. Okay, so we'll start with the join. What do you mean by joining factors? You studied, I think, database before, right? In databases, we do a join operation. Joining factors here is exactly like a database join, because the factors are tables, right? Tables with columns. So when we join two tables on a specific variable, we join on a specific column. Okay, so we'll build a new factor over the union of the variables involved. Let's see an example. I have these two factors, P of R and P of T given R. I want to join them on R. So we always join on one variable. If we want to join on multiple variables, we take one by one. So we'll join on R, okay, which means that I will take two tables and join them. In database, how do we do the join? We take every row here and match it with the rows in the other table that have the same value of the joining variable. So the joining variable here is R. So we'll take this row and match it with, or find out in the other table, the rows that have the same value of this value. So we'll do it with that row and that row. What will we do with these rows? We will multiply the probabilities. So we'll take this row, and of course this will match this row, which give us plus R in the new factor, plus R plus T, and 0.1 times 0.8, which is 0.08. Now continue with the same row here. This row will match also because we have plus R here, right? So it will be plus R. Now it will be minus T. And the value, the probability, will be 0.1 times 0.2, which is 0.02. And so on. Now this is a factor of R and T. We take the variables that appear before the condition, and then we put after the condition the remaining variables. Okay, we don't have any remaining variables after we take R and T now. So that's a factor of R and T. Okay, so we join them, we get a table out of the join operation. It's exactly like database join. If you are familiar with database join, joining factors is done for you. If not, then I explained how. You take every you match together, or you multiply the probabilities of the rows that have common values of the joining variable. So here we join on R, so we'll find this is plus R and these are plus R, so we multiply the probabilities. Here this is minus R, so we'll find out this is minus R, this is minus R, so multiply 0.9 with 0.1, we put here 0.09, multiply 0.9 with 0.9, we put here 0.81, and that's it, by the way. That's the whole table now. So that's minus R plus T, and that's minus R minus T. That's the entire factor, the new factor. Okay, so that's R, that's T. Okay, any question about joining? So out of this, now we have F of R. Usually you say F of R and T, but here it is actually the probability. That's the join probability. Okay, but generally we can just use F because it might not be a probability distribution. Okay, and that's the table that we get. Any questions about how we do the joining? Any questions? Is it clear? Okay, good. So we call the new factor, we indicate it by a node that has the variables here, that's r and t. So instead of having r pointing to t, here we have now r and t only. Okay, so that's joining. Type. Now, can we generalize this to do multiple joins? Of course, we can do them sequentially. So we join these, we get that. We join another one, we get a bigger one. So whenever we join join on a variable, we get a bigger table. Okay, so keep that in mind. Joining means we get a bigger table. So here is an example of multiple joins. We start with the 3 CPTs. Now we want to join on R. When we join on R, we get a factor that has R and T. So that's the same thing that we did in the previous example. Now, just one point before we do this. So generally, when we join on a variable, we first, among the factors that we have currently, we select the factors that involve that variable. So among these 3 factors that we start with, this one has R, this one has R, this one doesn't have R. So this one will not change, will continue with us as it is. So that's P of L given T. But now to join on R, we get these tables and join them together into one table. So now the new base net will look like that. R and T point to L. But of course it's not exactly a base net, right? Because so it's no longer a base net. It's just the nodes now look like that. Okay, so it's like we, instead of having two nodes here, we just have one node. Okay, but still we have here P of R and T, and we have P of L given T here. So these are the factors that we have now. Now, if I asked you to join on T next, what would we do? We select again the factors that involve T. Currently I have 2 factors only. Both of them actually involve T, because we have T here, we have T here. So we will join them on T. How would we join them on T? That's again the same way of joining databases, joining in database tables. So we'll take this row. Remember, we are joining on T, right? So we'll match this table, we'll join this row with all the rows that have plus T. So that has plus T, that has plus T. So here we'll have plus R, plus T, and plus L. And the value of that row will be 0.08 times 0.3, which is, I think, 0.024. Then this row with this row. So that will be plus R minus T, plus T also, and minus L. So that will be 0.08 times 0.7, which is 0.056. Right? I guess that. Yes. So that's how we do the join on T. And of course we continue. Type. What is the dimension of this factor? What is that factor first? How can we call it? So that's a factor of what? We are joining RT and L given T. So that's RTL. Oh, sorry, RTL. And then, so we put all the variables that are not conditioned. Then we put all the remaining variables. We don't have any remaining variables, so that's factor of R and T and L. Type. What is the dimension of that factor? Look how many variables here are capital letters. 3, right? So that's the 3-dimensional, which means the number of rows is d to the power 3. D is the number of values for each. Here we are talking about binary variables, so it's 2 to the power 3 or 8 rows. Here we have just 2 variables, 2 capital letters. So it's 2-dimensional. And so on. Okay, so here we have P of R and TLN, and that's the entire table. Any question about joining? So multiple join here means 1 by 1. Type, what if we are joining on a factor, on a variable, and we found out that the factors that involve that variable is more than 3. يعني, let's say مثلا I have a factor of A, a factor of B given A, a factor of C given B and D. No, let me change this. Okay, so I want to join all of them on A, because A is common here, right? So we have 3 factors, all of them involve A. I want to join them. What will I get out of this? First, what will I get out of this, and then how will I do the join? What I will get out of this is a new factor, and we said that it should have the union of all the unconditioned variables, then conditioned by the rest. So what are the unconditioned variables? A, B, C. So we'll have A, B, C given D, because D didn't appear here and appeared after the condition. So that's the only remaining variable. So that will be a factor of A, B, C, and D. Type, what is the dimension of that? What is the size of that factor? That's 4 dimensions, because we have 4 variables here, all capital letters. If one of them is small letter, which means that it is assigned a value, then it would be eliminated. It would be ignored in terms of the size. But here we have 4 variables, so the size of that factor is 4-dimensional. In terms of rows, that's if all the variables are binary, it will be 2 to the power 4, which is 16. Type. The main question remains, which is how we will do the join. We know that the factor eventually will be A, B, C given D, but how will we do the join? Do the join one step at a time. So you can join these 2 first, and then the result, join it with the third one. And that will give you this factor. Doesn't matter the order, by the way. You can join these first and then join the result with that. It doesn't matter. But if you join multiple factors on the same variable, do them one by one. Every 2, not any 2, and then the result with another 1, and so on. So sequentially. We did it in that slide, but in that slide we joined on 2 different variables. It's the same thing if you have a variable, but with multiple factors, you do them one by one. Any questions about this? Any questions? So joining is clear? Can you raise your hand, please, if everything is clear so far? How about the others? Okay, right, a bit more than 50% is okay. The others didn't say anything, so I will assume that it's okay with them. Okay, type. You can lower your hands now. Okay, now, so we are done with join. We said that we have 2 building blocks, joining, and the other one is elimination. So what do we mean by elimination? We already studied elimination before, which we called it at the time marginalization. So what do we do in elimination or marginalization? We take a factor and sum out a variable. We eliminate one variable, which means that we will get a smaller table. So we'll shrink the big table into a bit smaller table. How we do that? Here's an example. Let's say that we have this factor P of R and T, and I want to eliminate R. So eliminate R means sum over R. And let me show you one very, I think, simple way to do that. We want to eliminate R, right? So let's eliminate R from the table. Are we done? Of course not. When we eliminate R, now we will find out that some rows have the same exact value for the variables. So, for example, this row has plus T, and this row has plus T, right? I mean, same combination, of course, if we have more than one variable. So we'll sum these together. So in the resulting table, we will have plus T, and here we will have this value plus this value, which is, I think, 0.17. And then we will sum out these two values because they have the common value. So minus T will get 0.02 and 0.81, which is 0.83. So now this is a new factor which has only what? We eliminated R from here, so we'll have only T. You can call it P of T, of course, if we have P of R and T here. So that's elimination. Very straightforward. Just cross over the column of the variable that you want to eliminate and sum out the rows that have now the same combination of values for the other variables. Okay, we saw that before, of course, earlier in this session. So out of this we'll get P of T, which is, now you see, it's like shrinking, right? So you see in the figure here, that's nice, very nice figures from Berkeley, that starting from a big factor, we now with the marginalization, we shrink it into smaller factors by getting rid of one dimension from the table. Now we can also do multiple eliminations. So if I have this big table, we can eliminate one variable, we get smaller. We eliminate another one, we get even smaller. Okay, so let's see that. We want to now to eliminate R from that table. How do we eliminate R? Okay, now we cross over this column. When we cross over this column, now we have plus R and plus L. So we'll add the probabilities for plus R and plus L. So we have plus R and plus L here. We have plus R and plus L here. So that will be the sum of these. So we'll have plus R plus L and 0.026, I think. And same for the others. So how many rows we'll have here? What is the size of that factor? Now that factor will have only T and L, right? So we'll expect that this is two dimensions. We call that two dimensions because we have two capital variables, two dimensions. If each one is binary, then we will have just 4 rows. So this 8 row table will have 4 row table, shrinking by elimination. Okay. Now, if I want to get rid of T, eliminate T also, again, we will cross over T, we'll sum over the same values for the rows, we'll get now only 2 rows, which indicate P of L. So from RT and L, we got RT, we got TL, and then we got L only. Okay. Any questions on elimination? Yes, Sad. Sorry, I don't hear you. Ah, yes. Yeah. Sorry. Yeah. Yeah, that was my mistake. Sorry. Yeah. Okay, let let me erase this. Okay, so yes, so we sum out R, so we'll just cross R. Okay, just cross R. When we sum out T, we cross T here. Yes, you're right. Thank you. Any other questions? So in fact, we will have plus T plus L and plus T plus L. So we'll sum these together. That will give us 0.01, 0.051. Yes. Thank you, Saad. Any other questions? Okay, very good. Time. Now, putting the building blocks together. When we do inference by enumeration, we do multiple joins. We join all the hidden variables one by one. Whenever we join, we get the table will increase, right? The size of the table will increase. The size of the factors will increase. And then we eliminate one by one of the hidden variables. So we marginalize over the hidden variables. We do multiple sequential joins, join, then eliminate to get what we want eventually. So that's the main idea of inference by enumeration. We join everything, we join all the hidden variables to get the joint distribution. So that's actually the big joint distribution of all variables. Join, assuming here that we have 3 variables only, and then shrink, or eliminate to get only the variable that, or the variables that we care about, to get the probability that we want to infer eventually. Let's see an example. I think we will. Yeah, we will see an example. Okay, but let's before we see an example, let's compare between inference by enumeration and variable elimination. So in inference by enumeration, we join all the hidden variables before we eliminate them. In variable elimination, we join on a variable and then immediately eliminate it. Then join on another variable, then eliminate it. Then join on another variable, then eliminate it. Okay, so we interleave the join and elimination. In inference by enumeration, we do multiple joins consecutively and then multiple elimination consecutively. Type, what's the difference? I mean, it seems like they are the same. The difference is very clear from even this nice figures. If you look here, when we join, the tables will increase in size. When we continue joining, when we join multiple variables one by one sequentially, the factors that we are processing will increase in size exponentially. Okay, so the complexity will be dominated by the biggest factor. But when we do variable elimination, we don't let the factors increase in size too much. Why? Because we join on one variable and then we eliminate it. Then we join on one variable, then we eliminate it. Okay, immediately. So the size of the factors will be kind of controlled, will be much smaller than the biggest factor that we will have eventually when we do an inference by enumeration. Okay, so that's the main idea. Let's go through an example. Back to the example of the raining traffic lateness, and let's say that I want to get P of L. Inference by enumeration, as I said, we'll do joins and then elimination. So mathematically, we will do the following. We want to get, remember what we saw earlier in this lecture, that P of L is equal to sum over T and R of the probability of T, R, and L. Or let me write it the other way. The other order doesn't matter, but the order of the variables here, which is it's RT and L. Okay, RT and L. Okay, so that's the joint probability, and that's the marginalization. So if we look at this form, it looks like that we need to compute this probability first, which is the big joint table, and then do the marginalization using by summing over T and R. So that's exactly what we see here. Okay, but the only thing is that we factored out this joint probability using BaseNet, using the conditional independence that is encoded by the BaseNet. So P of R, T, and L, we can spread it out by the chain rule, but we can also use the what is encoded by the BaseNet. So this joint probability is probability of L given T times probability of R times probability of T given R. Okay, so this is P of R, T, and L. That's what we want to get first, then we sum over T and R. Okay, so what we will do in inference by enumeration using factors is that we will join on R. Remember, the idea is to join on all hidden variables. What are the hidden variables here? R and T. So we'll join on R. This step will give us what? Will give us a factor on R and T, right? Because we join on R here, we get R and T. And then we join on T. So we join this with this. This will give us a factor of R, T from here and L from here, right? So that's R, T, and L. That's the biggest factor. Then we eliminate on R. When we eliminate on R, we get rid of R, we get F of T and L. And then we eliminate T, we'll get F of L only, which is what we want. That's inference by elimination. We join on every hidden variable first, and then we eliminate them. Now let's compare that with variable elimination. In variable elimination, what we will exactly do is to move the sum operation into its closest position. Yani, if you look at this form, you will see that this factor doesn't include R. So I can actually move this sum here. And that's exactly what we did here. So that's now the sum went over these two factors, and then the result will be summed with this one. Will be joined and then summed. So variable elimination means that we will join first on one variable. So this will give us a factor of R and T. Then the sum over T will eliminate T. Sum over R will eliminate R. So we'll get here F of T. Then we'll join this one with this one. So we'll get a factor of L and T. Then we eliminate T because we sum over T here. So we'll get a factor of L eventually, which is what we want. So variable elimination is just a manipulation of the operations, interleaving joining with elimination, but will give us, of course, the same exact value of inference by enumeration. If that's the case, then what is the idea of variable elimination then? What's the advantage? The advantage is that we will not keep around big factors. And you look at the sequence here. This is what we want. So I will just erase it. So look at the sequence of factors here. FR and T, FRTL. That's the biggest one. That's the thing that we don't want. But here the biggest factor was only 2 dimensions. Here we have 3 dimensions. Of course, that's just an example on over 3 variables. If we have many variables, that will be really huge. So that's the biggest advantage of variable elimination, that it will keep the size of the factors kind of under control. It's much smaller than the biggest factor that we will get if we will do inference by enumeration. This slide is very important because it shows you that mathematically they are the same, but manipulation of the order of operations will make one to be more efficient than the other. Okay? Any question about this? This is very important to understand because that's the mathematical explanation of what we will be doing over factors. Yani when we talked about join and elimination, maybe you don't understand why we are saying that. Now you understand, I hope. the relation between the mathematical operation and what we will do visually on the tables. Okay, any questions about that? Is the difference here clear? Okay, good. Right. Now let's see an example of variable elimination or marginalizing early. When we say marginalizing early, when we talk about variable elimination, whenever we join on a variable, we will immediately eliminate it. Okay, so here we will join on R. So remember, whenever we join on a variable, we get the factors that involve it. Where are the factors that involve R here? This is this one and this one. But this one doesn't. So we will keep it as it is, and then we join these two, we'll get, so these two, we will get this one, R and T. Now we have this one and this one, right? Whenever we join, we eliminate immediately. So we'll eliminate here R, we get only T. So now we have T and R and L only. We have P of T and P of L given T. Okay, now we can join on T. That's the second hidden variable. Remember here we are asking about P of L. Okay, so we'll join on T. Now where are the factors that involve T? Both. We have T here, we have T here. So these two will give us a factor of T and L. Okay, this one. And then immediately we'll eliminate T. Why do we eliminate T? Because we joined on T here. Remember, in variable elimination, we join and eliminate immediately on the same variable. So when we eliminate T from here, we will get L only. We'll get L only. So that's what we want. That's what we want. Okay. Type. That's when we don't have any evidence. So we started with the initial CPTs of the base net. When we have evidence, we will just select from the factors the rows that match the evidence. So if we don't have evidence, we start with the initial factors. If we have evidence like that, let's say that we have plus R, so we'll keep only plus R from here. We'll keep only plus R from here. So we get rid of this. So, and we don't have any R here. So we start with these three factors. Notice that that was P of R capital. That's now P of plus R. This is P of T given R, which means that this is 2 dimensions. Now this is 1 dimension. It's P of T capital given plus R. Okay, and that's the same. So that's actually will be the first step. Whenever we have evidence, is to select from the tables, the initial CPTs, all the rows that match the evidence. And these will be the initial factors that we will start with. Then we eliminate all variables. When we say eliminate, it means we join on each one, we pick one, we join on it, and immediately eliminate it. We pick another one, we join on it, immediately eliminate it. We do that for all hidden variables, which means the variables other than the query and the evidence. Okay? So we will, the result will be, eventually after we do that, after we do join and elimination on all hidden variables, we will have something like this. We will have a joint factor for all query and evidence variables. It's a selected join. It's a selected joint of query and evidence. That's what we will get eventually. Now, the only remaining step is to normalize. So to get our answer, we just normalize. How do we do normalization? We studied that before, right? So we'll just sum these two values and divide each one of the sum. So we'll get P of L given plus R. Right. Why do we do this normalization? This is a joint probability of plus R and L. Okay? So if you remember, this probability P of, let me do it here, P of L given plus R is equal to P of L and plus R over P of plus R. Where is P of L plus R? These are the two values here. And where is P of plus R? This is the sum of the values. So that's the normalization that we do to get P of L given plus R. So that will be the last step. And that's it. That's it for the steps. So let me summarize all of what we have studied today before we give a full example. If I have a query like this, P of Q given some evidence. So that's the query. That's the query, and that's the evidence variables. I want to compute this probability table. That's a conditional probability table. Okay, conditional distribution of Q, given all of these values. The first step is to start with initial factors instantiated by the evidence. What do we mean by instantiated by the evidence? We'll select only the rows that match the evidence. That will be the initial factors that I will start with. The second step is to get rid of all hidden variables. How? Pick one, join on that variable, immediately eliminate it. Pick another one, join on it, eliminate it. Pick a third one, join on it, eliminate it. Until we get rid of all or eliminate all hidden variables. After we eliminate all hidden variables, we will still have some factors alive. We join all of these factors. We join all of these factors and then normalize. So that's the third. That's the third step here. Third and the last step here. Okay, so that's the whole general variable elimination procedure. Start with initial factors instantiated by the evidence. Eliminate all the hidden variables by joining them, then eliminating them one by one, and then join all remaining factors and normalize. Now let me go through an example, and then I will open, inshallah, the door for questions. So let's say that I have this classical alarm burglary alarm base net, and I want to compute this probability. P of B given J small M small. So here assume that we have plus here. Okay, so J small M small means plus J and plus M. Okay, so that means that we have evidence here. So we have to start with the factors instantiated by the evidence. What are the initial factors here of base net? We have P of B, we have P of E, we have P of A given B and E, we have P of M given A, and we have P of J given A. Of course, you understand how I got this from the base net, right? So that's the probability of every variable conditioned by its parent or its parents. Okay, so the first step in variable elimination, given that I want to get this probability, is to instantiate the initial instantiate the initial factors by the evidence. So instead of having, so P of B will not be affected, right? Because it doesn't have J and M, right? So we have the evidence here is J and M. So I want to instantiate this factor because it has M, and this factor it has J. The others will not change. So we have P of B, P of E, P of A given B and E. This will not change. Here, instead of P of J capital, I will have J small because that's plus J. So that's P of J plus J given A, and that's P of plus M given A. Okay? Right. These are the initial factors. Now, I want to do variable elimination. Choose an order of variables, of the hidden variables. What are the hidden variables here, by the way? What are the hidden variables? We have the query is B, the evidence is J and M, so the hidden variables are all the remaining ones. What are the remaining ones? A and E, right? A and E. So we'll have to eliminate A and eliminate E. So here we chose to start with A. So we will eliminate A first. To eliminate A first, we have to determine which factors involve A. Where are the factors that involve A? This one, and this one. Right? So we have these three factors, P of A given B, E, P of J given A, P of M given A, and now we will join them. When we join them, what will we get? We'll get a factor of A, J, M, given the remaining ones, B, E, and of course A is already used. So that's the factor that we will get from joining these three factors on A. So we'll get this one, P of JMA given BE. Now remember, when we join, we immediately eliminate. Which variable will eliminate? The same one that we joined on, which is A. So we'll eliminate A from here. We get P of J M small or plus J plus M given B and E. Okay, so what are the factors that are remaining now? Remember, we joined all of these factors. Khalas. Instead of these factors, we have this one. So we have this one and eliminate, of course. So we have this one and which ones? And this one and this one. These three were already joined into this one. Okay, so we have these three factors. We'll start with them. So P of B, P of E, P of J, M given BE. Now the second step is to eliminate the other hidden variable, which is E. So eliminating E means finding out which ones involve E, which is P of E, P of J, M given BE. Join, we get P of E, J, M, E, J, M given B. And then we eliminate E, get rid of this E, then we'll get P of J, M given B. Okay, we still have P of B, by the way. So out of this, we'll have two factors now, P of B and P of J, M given B. Do we have to join any more? Join any hidden variables? We are done with the hidden variables. So now we join everything we have and then normalize. Right. Join on what? Join on what? Join on the common variable. So here we have B, so we'll join on B. We'll get P of J and B out of joining these two factors. Should we do any elimination? No, don't eliminate anything because these are the variables that we want. We want to keep them. So what we need to do now is the last step, which is normalization to get the probability that we want. Okay? Any questions? So now you know how to do any inference given the base net, given the initial factors. You know that you are given the query and the evidence. You can compute any probability using this procedure. Select the evidence, join and eliminate on every hidden variable, join all factors that remain, and normalize. You will get what you want. Any questions on that procedure? This is very important. That's the main idea of variable elimination and inference using BaseNet. And as I said, you can do it mathematically, of course, but this way of variable elimination and factors is much easier than doing it mathematically, because whenever you have a very large number of variables, that will be really a headache to do. Okay, but using factors will be much easier. And don't forget that this marginalization or elimination means that you get the sum. So for this one, if you eliminate, you are talking about eliminating E, so that means that you will get sum of this over E. If you are asked at any time on how you eliminate that variable, you do it that way. So that's the factor that you get. You sum over all values of the variable that you eliminate. Any questions? Okay, so we just have a couple of slides remaining here to say something about efficiency, and then we will switch to the last subtopic, which is sampling, which is doing inference that is even more efficient than variable elimination, but it has its own disadvantage that inshallah we'll talk about next time. So inshallah we'll stop here. Talk to you on Thursday. Assalamu alaikum wa rahmatullahi wa barakatuh.